Today, we're diving into a hidden language. It's a set of rules that, believe it or not, connects a high-speed car chase, a perfect basketball shot, and even the swirling currents of the ocean. It's the language of motion, and it is absolutely everywhere.
I mean, really think about that for a second. These three things, they seem like they're from totally different worlds, right? One is all about speed and strategy. Another is about pure athletic precision. And the last one, well, that's about the immense, almost chaotic power of nature. So what in the world could they possibly have in common?
Well, the big reveal is this. All of them, no matter how different they seem, are governed by the exact same set of physical laws. We can actually describe, predict, and even control them using one single incredibly powerful branch of physics.
So, to really understand this language, we first need to learn its grammar. The foundational rules that dictate how everything gets from point A to point B. And that grammar is called kinematics. It's the part of physics that's completely obsessed with the how of motion, not the why. We don't really care what's pushing or pulling something, we just want to describe the movement itself, how fast it's going, how far it's gone, and in what direction.
And this is our toolkit. Now I know, it might look like a bunch of intimidating math, but these 4 equations are the absolute heart of kinematics. They connect just 4 key ideas. You've got displacement, which is just a fancy word for how an object's position has changed, velocity, which is its speed and direction, acceleration, which is how fast that velocity is changing, and of course, time. With just these 4 tools, we can solve an incredible range of problems.
So let's put our new toolkit to the test, shall we? We'll use a classic, real-world scenario, a high-stakes chase on a long, straight road. We're going to keep it simple for now, just motion in one dimension.
So here's the setup. We have 2 cars on the highway, car A and car B. Car A is trying to catch up. Now, car A is faster and it's accelerating, but car B has a head start, although it's actually slowing down. This table lays out all the key info we need, their starting positions, speeds, and how they're accelerating. And this is the million-dollar question we want to answer. The key, the whole trick, is to realize that at the exact moment car A overtakes car B, they have to be in the same place at the same time. So we can use our kinematic equations, write out an expression for each car's position, set them equal to each other, and solve for time.
And the answer is just under 12 seconds. That's it. That's all the time it takes for car A to finally catch up. But that's only half the story, right? We also need to know where on the road this little drama unfolds.
A little over 1,000 feet from where car A started. See, by plugging that time, that 11.89 seconds, back into the position equation for either car, we can pinpoint the exact spot on the highway. And just like that, problem solved.
Okay, so a straight line is one thing. But, the world isn't just one-dimensional. So let's level up and see how these same rules apply to something moving through a plane, like the beautiful arc of a perfect basketball shot.
Now, here is the secret. This is the big aha moment. It looks way more complicated, but it's really not. The key is to just break the motion down into 2 totally separate independent parts, its horizontal motion and its vertical motion. So instead of one complex problem, we just solve 2 simple ones.
Let's look at these 2 components. Horizontally, once that ball leaves the player's hands, there's pretty much nothing pushing or pulling it forward, so its horizontal speed just stays constant. But vertically is a different story. Gravity is always pulling it down. That means its upward speed slows down until it hits the very peak of its arc, and then it starts speeding up on its way back down.
And here's a cool takeaway from all this physics. If you want to throw a ball as far as you possibly can, the math of these 2 components tells us that the perfect, optimal launch angle is exactly 45 degrees. It's the absolute perfect balance between upward motion, which gives you hang time, and forward motion, which gives you distance. So, we've handled one object, then an object in 2 dimensions. But what if we're dealing with something that's made of, well, countless individual particles, all moving together, like water in a river, or the air in our atmosphere? This is where we step into the amazing and complex world of fluid dynamics.
All of a sudden, our simple approach of just tracking one thing, well, it doesn't seem very practical anymore, does it? Whether you're talking about the swirl of cream in your coffee or the vast currents of the ocean, we're now dealing with a continuum of stuff. How do you even begin to describe that kind of motion?
It's like the physicist Jim Price said, the physics itself isn't really new. It's still just classical mechanics. The real head-scratcher, the huge challenge, is the mind-bogglingly complex kinematics.
It's just the sheer difficulty of describing the motion of so many interacting parts that makes fluid dynamics one of the great frontiers of science.
So, to tackle this insane complexity, physicists got clever. They developed two powerful and very different ways of looking at the exact same flow. Two totally distinct points of view.
Here's a great way to think about it. Imagine you're analyzing a football game. You could choose to follow one specific player. Your eyes are locked on them, no matter where they go on the field. Or you could do something else. You could fix your gaze on one spot, say the 50-yard line, and just describe all the players who happen to run past that point. Both methods describe the game, but from completely different perspectives.
In physics, we call these two perspectives the Lagrangian and Eulerian frameworks. The Lagrangian view, that's like following that one football player. You track the path of an individual particle of fluid over time. The Eulerian view, on the other hand, is like watching the 50-yard line. You stay in one fixed place and just observe the fluid as it flows past you. Both are incredibly powerful ways to describe the exact same motion. Now, here is the most crucial point, the thing you have to remember. Neither view is more correct than the other one. They are just different descriptive tools. And what's more, they're mathematically transformable. You can always convert a complete Lagrangian description into a complete Eulerian one, and vice versa. It's all about picking the right tool for the job you're trying to do. And just like that, look at the journey we've taken. We've seen how a few core principles can be scaled up, from a simple one-dimensional chase to a two-dimensional arc, all the way to describing the mind-bendingly complex flow of the ocean using two totally different points of view. It's all built on the same set of grammatical rules. In this language, it isn't just theoretical stuff for a textbook. It's used every single day to predict the weather, to design airplanes, to program the movements of robots. It is, quite literally, the fundamental code we use to describe our physical world. So the only question left is, now that you know the basics, what motion will you describe next?